All right, so guys, I know it's been a super long time since we've been together. I don't know how concerned or connected you are to where we were before we left for break. But guys, if you're connected with what we're doing, you should have 3 questions that are running through your mind. Here are the answers to your 3 questions. You ready? Today after school, Wednesday, and I have no idea. So what were the questions? So you're going to take a shot at it, Zach? Go ahead. What was question number 1 to which the answer was today after school?
Remake or the...
Incorrect. Question number 1 is, when are your extra credit projects going to be graded? And guys, the answer is today after school during 4th period. Miss Call and I have a shared prep period, and we're going to gather together and grade these. So question number 1, when will your extra credit be graded? Today after school. Question number 2, the answer was Wednesday. Try that one. All right, I'll take it from here. When are you going to get your tests back? So, guys, last time in class we took a test. If you were not here, obviously you need to take that test. And guys, I would strongly encourage you to take it before Wednesday, simply because then you can still do remediation. Today after school is a lovely opportunity to take the test. If that doesn't work for you, make other arrangements. But guys, you really want to take this before Wednesday. But guys, I will have your test to hand back to you on Wednesday. Frankly, they're almost great. They're graded but not totaled. So they are kind of done. But today, it's better to hand them back to you on Wednesday. You'll see when we look at December. So guys, I'll have your test back for you on Wednesday, and then we'll go into remediation from there. And then guys, question number 3, the answer to which was, I have no idea. The question is, when are we getting your papers back? And guys, I don't know. Obviously, we need them back so that you have time to rewrite them. But literally, I slid them into a drawer down in the front office, and they just magically went away. And they should be on their way back. So I'm going to go down and talk with Ellingford today, find out when they'll be back. But right now, I have no idea. But if you didn't submit your paper initially, again, you'll just submit it with the rewrites. If you choose to rewrite your paper, we'll see. I don't know. They'd better be here this week, but we'll see. So, again, guys, extra credit today, tests on Wednesday, and then rewrites as soon as they're graded. So, questions that you have that weren't on my mind. You guys okay? Okay. So, guys, what I'd like to do then is I'd like to look at the calendar with you moving forward. Because, guys, please, in all of your classes, don't lose sight of this. Guys, today we're going to start this next unit. And then, holy smokes, you guys, we got 3 weeks and the quarter's over. And I know that we're leaning heavily towards Christmas break and we're excited to get there. Nobody more than me. But guys, please be really careful with this. Literally 3 weeks to determine your second quarter grades. So guys, keep an eye on this. Relative to our class, the way that this worked out is the unit test for this unit that we're starting today will go on third quarter's grade. We will take it before Christmas, so you don't have to remember stuff over Christmas break. But guys, we won't have time to remediate this test, which means we'll take it right before Christmas break, but it'll go on third quarter's grade. So that works out well for you, in that the test isn't right after we get back from Christmas, but it does mean the test we just took is the last test on second quarter's grade. So guys, from there, on Wednesday, we're going to do a lab, which completely reinforces everything you're learning today. Then Friday is new material. Tuesday is new material. Thursday is the last of the new material. Then we have a lab on the 13th, test on the 15th. And then, guys, we have another lab right before Christmas break. So you've got like 3 homework assignments and 2 labs still up in this quarter's grade. And then, guys, we're going to be done with second quarter. So, questions about any of that calendar stuff? You guys all good? You'll ask if you're not, right? You guys good? Okay. All right. So, guys, do this. Grab your note sheet and let's get going. Here we go. So we need this. And, guys, we're going to really sort of lay this out for you to help you be successful with this stuff. So guys, the topic for your notes today is periodic trends. The date today, I have no idea. What's today? 29th? Guys, the day, is it you guys, yeah, it's the 29th. And guys, let me sort of lay out the day for you today. Guys, what we're going to do today is we're going to dig deeper into the things that we understand about the periodic table. During the last unit, we figured out how to connect Lewis dot structures to locations on the periodic table. We know that all of these have 1 dot, 2 dot, 2 dot, 3, 4, 5, 6, 7, and 8 dots. But guys, we're going to dig into that even more deeply today. And we're going to look at trends on the periodic table. In order to help you do this, guys, do this with me. So guys, here's your paper. And I'm going to help you structure your notes so that you can make this all fit and fit well. So guys, again, you're going to, the first thing you're going to do is draw a skeleton of the periodic table in your notes. But guys, notice the way it's lined up. It's going to start a little bit left of center. It's going to go about a third of the way down the page. And then all you're going to do is you're going to break up the S sublevel into its 2 columns, the P sublevel into its 6 columns. You can leave the D sublevel undivided. Then guys, after that, you're going to skip down 6 lines and you're going to draw in the F sublevel down 6 lines. So guys, let me pause for a minute. Let me let you catch up, and then we're going to dig in and I'll explain to you how today is going to work. So have any of you guys turned in papers for your English classes that go to the graders? How long does it take to get them back, Zach? Normally, do you know?
It takes about a week.
A week? Has anyone else had experience with that? I have no idea what to expect. We'll see. You guys, I'll give you another second. And guys, by the way, when you're setting up these columns, you're going to find in a minute they're called groups. You want to make them maybe clean enough that you can write in them, because we're going to be labeling this periodic table. So have some space that you can write in. It should look like this. If it does, you'll be fine. You need another minute? Is that too dark here? Let me turn, now that you see what this should look like, we're going to need these on anyway. All right. You guys all done? Need another second? Okay. You guys good? Okay, so one more thing just to sort of set the stage for you. So guys, as you're setting this up, let me just be clear with you. So as we start to take what you're drawing and collect all the information you need, guys, this space right here, do not write in this space until I tell you to. And these 6 spaces between the body and the F sublevel, guys, don't touch this space either until I tell you to. So guys, this is hallowed ground. This is hallowed ground. And so as you're taking notes, what you're going to do is your notes are going to be down here, and we're going to get into this space later, but protected it first, because you're going to see that that's where we're going to put the trends, and you're going to need some clean space in order to do that. So this is going to be your note space at first. All right, you guys good to go? All All right, so guys, let me explain to you then the way today is going to work. So what we're going to do today is we're going to do some really foundational stuff about the periodic table. So the first thing we're going to do is I'm going to share some terms with you. And guys, these terms are going to show up right here, but you're going to write them down here because you're not going to mess with this space. So guys, first of all, terms, you're going to write them down here. Then we're going to label our periodic table, and you'll just do that in the periodic table. And guys, this is all just going to be secretarial. You just need to write this stuff down. No thinking, really nothing interesting. You just got to get it on paper. Then guys, after that, we're going to move into the space to the left and below the periodic table. And we're going to be developing some ideas that are going to sort of build on each other. And we'll talk about that as we go. So guys, watch how this is going to change. So now what I've done is I've zoomed into the periodic table and I brought the F sublevel up. Obviously, you're not going to do this, but it works out just great. And now, guys, the terms that you need to know, and you're going to write them down in your note space. So, guys, the first term that you need to know is the term period. So down in your note space below the F sublevel, and guys, periods are the horizontal rows on the periodic table. And again, guys, you're not writing this where it appears on my screen. I just didn't have anywhere else to put it, so I put it there. So guys, I know it's been a week, but let's make the connection. How many periods are there in the periodic table? And yours are already numbered. How many are there? There are 7, and those relate to the energy levels. So guys, when we numbered 1 through 7, the energy levels, what we were actually doing was numbering the periods on the periodic table. So we're going to call them periods and not energy levels. So then guys, after that, we've got groups. Groups are the vertical columns on the periodic table. So guys, this is maybe a stretch, but I'm thinking you're going to figure this out. Guys, what do all the elements in a group have in common on the periodic table? Not phase. Think about Lewis dot structures. Guys, what do all the elements in a group have in common? Same number of what kind of electrons? Do you remember? Yeah, valence electrons. So guys, all of these have 1 electron, valence electron. These have 2. These have 3, 4, 5, 6, 7, and 8. So guys, all the elements in a group have the same number of valence electrons, and as a result, they all react similarly. And we're going to dig into that more in the coming days. So guys, that's it. Those are the only 2 terms that you need to know. You need to know that the periods are horizontal. There are 7 of them. The groups are vertical. They have the same number of valence electrons, and therefore they react the same. Periods, groups, if you're good to go. You guys all caught up? Okay, now what we're going to do is this. We're going to label the periodic table. So I'm going to make this go away if you're okay. I know it's early. Is okay? All right, so guys, that's going to go away. And now we're going to start labeling the periodic table. So guys, we're going to go groups 1 and 2, 3, 4, 5, 6, 7, and 8. So guys, number the groups on your skeleton of your periodic table. So guys, there's lots of different ways to number the groups on your periodic table. You'll notice that on your periodic tables, one of them's got Roman numerals, and it does go 1, 2, 3, 4, 5, 6, 7, and 8. But there's another way to do it with Arabic numbers, 1, 2, and it goes through 18 because it includes the D. Guys, we're just going to go 1 and 2, skip the D, and then 3 through 8, because these numbers tell us how many valence electrons are in these groups. And we're going to skip the D because we don't do a lot of D-level chemistry. So just 1 and 2 and 3 through 8. You guys good there? Okay. Now, guys, each one of these groups on the periodic table has a name. You don't need to know them all. You just need to know 1 and 2 and 7 and 8. 3 through 6 also have names, but we don't need to know them. So, guys, you just need to know the names of 1 and 2 and 7 and 8, but you already know group 8, so let's do that right now. What's group 8? Noble gases. So let's hit that guy. Noble gas abbreviations. And then, guys, let's pick up the rest of these. I know that this is mindless. We're almost done. We'll just get through this. Again, terms you need to know. But there's not a lot of thinking going on here. But that'll change in a minute. So guys, you need to know 1 and 2, 7 and 8. So let's go to group 1. Guys, these are called the alkali metals. Everything on the left-hand side of the periodic table is a metal. We'll talk more about that later. But guys, these are what are called the alkali metals. Then let me just give you group 2. Group 2 are called the alkaline earth metals. But I didn't have space to put metals. You can just call them the alkaline earths. But these are the alkali metals, and these are the alkaline earth metals. And then guys, let me just, actually, we're not going to skip to group 7 yet, so we'll slow down for a second. So you've got the alkali metals, the alkaline earth metals, the noble gases. Before we go to group 7, we need to talk about the D sublevel. Guys, that entire thing are what are called the transition metals. They transition between the S's and the P's, so we call that entire block the transition metals. Now, guys, we're ready for group 7. Maybe some of you have heard of these. These are called the halogens. And guys, we got 2 more to go. And then this is going to become less about taking notes and more about developing ideas. So guys, the last thing we need to do is this. We need to go down and label the F sublevel. And in order to do that, the logic behind it is this. So this guy right here comes after element number 57, and this is lanthanum. So they call these the lanthanoids. That sort of allows you to anchor it back to the body of the periodic table. So lanthanum takes us to the lanthanoids. And guys, if you look carefully at your periodic table, you can probably figure out the name of these given what they come after as well. Yeah, so the actiniumoids, they're called the actinoids. And guys, that's it. You need to know the alkali metals, the alkaline earth metals, the transition metals, the halogens, the noble gases, the lanthanoids, the actinoids. You need to know groups go up and down, periods go left and right. And if you can keep track of that, that's all the vocabulary you need. You guys good? Let me let you catch up, and then this is going to start to get interesting. You guys okay? Okay. So, guys, here's then what we're going to do. We're going to zoom out of this, and now we're going to develop a pattern. So, guys, let me explain to you how this is going to work. Can I zoom out? Because this is all going to go away. You guys good? Okay, so notice what I did. I got rid of the F sublevel because we don't need that anymore. You're not going to do that. It's just hanging out in your notes. But guys, remember your note space is still down below. But now, guys, we're going to start mucking around in this space left and below the periodic table. And when we're done with the day, here's what you're going to have. You're going to have 5 downward pointing arrows, and you're going to have 5 rightward pointing arrows. So guys, when you're drawing arrows, leave enough space that you can get 5 in there and then 5 down below. And guys, what we're going to do, this is how we're going to wrap up the day. We are going to talk about 5 trends that you need to know on the periodic table. And so the way the pattern is going to go is this. I'm going to define the trend, then we're going to draw in arrows, then we're going to identify the trend, then we're going to identify the overall trend, and then we'll just move to the next one. So guys, for example, the first trend that we're going to talk about is atomic number. So guys, do this with me. Go down in your notes underneath where you wrote groups and periods, and if you don't remember that the atomic number is the number of protons in the nucleus, you can write that down. But guys, write it down underneath where you wrote down groups and periods. But many of you know that the atomic number is the number of protons in the nucleus, and so you don't need to muck with it. But it's up to you. So guys, step 1, identify the thing that we're going to talk about, the trend. Now guys, whether you wrote that down or not, the next thing you're going to do is this. Draw a downward pointing arrow right to the left of your periodic table, and then a rightward pointing arrow right below your periodic table. Now guys, this is a huge stretch, but let's try. Do any of you happen to remember the abbreviation for atomic number? It is. Good for you. It's actually Z. Z is the atomic number. Now guys, do this. So we've identified the trend. We've talked about the abbreviation. Now we need to find the trend on the periodic table. So guys, grab your periodic tables. Let me grab one as well. Does anyone need one? Alex, did I get you one? Oh, good. Okay. So guys, grab your periodic tables, and if you don't remember, you can go down to the key in the bottom left-hand corner, and the atomic numbers, the big blue number in the upper left-hand corner. Guys, allow your eye to scan, first of all, notice we're using the term right, let your eye scan down the groups. As we go down a group, does the atomic number get bigger or smaller? Every time? Every single time. Do you see any exceptions where you go down a group and the atomic number gets smaller? There aren't any. So, guys, these go from smaller to larger every single time. But, guys, you'll notice they don't do this numerically. They go 1, 3, 11, 19, 2, 4, 12, 20. Guys, it's not like you're counting 1, 2, 3, 4, 5, but they do always get bigger from top to bottom. You settled on that? What about left to right? So guys, as we move left to right across the period, do the atomic numbers get bigger or smaller? Every single time? Every single time. So guys, these go from smaller to larger, moving left to right across the periodic table. So that is the trend in a group, small to large, and the trend in a period, small to large, moving down and left to right. You guys good? Now a new idea. Guys, given these two trends, where are the biggest atomic numbers on the periodic table? Bottom, yeah. So, and guys, if you're not sure, this is a big idea in a minute. We get larger down, we get larger right. So these are the biggest atomic numbers. These are the smallest atomic numbers. So these guys have the most protons on the periodic table. You guys good? Yeah, please. Interestingly, yes. In this case, it is because we read left to right and top to bottom, and they get bigger as we do both. But Zach, be careful with that because that's not always going to be the case. But in this case, it is. So guys, the most protons are bottom right. You guys good? Okay, next trend. So this is going to turn black, meaning we're not focusing on it. And guys, the next one we're going to do is atomic mass. So if you don't remember that the atomic mass is the number of protons and neutrons in an element, guys, maybe you want to write that down at the very bottom of your paper, but that's up to you. But guys, whether you choose to include this in your notes or not, you do need to do this. And guys, the arrows that we're looking at will always be blue. So do a downward pointing arrow and a rightward pointing arrow. Again, you're going to have 5 in total. This is really a stretch. Now we need to label the arrows. Do you remember the abbreviation for mass? Oh, good for you. It's A. Yeah. Okay. Now guys, following the pattern that we built before, we know that atomic mass is protons and neutrons. We know that the abbreviation for atomic mass is A. We've got our arrows drawn. And then guys, we're going to look on our periodic table, and the atomic mass or the atomic weight are the small numbers in red in each of these boxes. So guys, let's do groups first. As you go down a group, do the atomic masses get lighter or heavier? Just allow your eye to scan down the groups, find the trend. Do they get lighter or do they get heavier? Are there any exceptions where you move down and they get lighter? Do you see any? It's because there aren't any. So guys, when we go down a group, they always go lighter to heavier. So that's the trend. The light guys are at the top. The heavy guys are at the bottom. So now guys, again, keeping with the pattern, we now need to move left to right. So guys, grab your periodic tables, again looking at the small red numbers. As you move left to right, do these get lighter or heavier? What do you see? Are they getting lighter or heavier left to right? Heavier. But do you see the exceptions? There aren't many. Maro, I see you nodding your head. Can you point us to one? 109. I don't remember where they are. So hold on. So 109 here. Okay, so yeah, good for you. So we go 277. So we're going up, right? So 264, 277, and then it goes down to 268. So we've added a proton, but the element is lighter. Guys, do you see any others where you move to the right and it goes down? I don't remember where they are. Zach, just a second, Ryan, do you see one? Yeah, so I sort of stumbled on that one too. So here we go 240, 109, up here. So we go 264, 266, and then down to 264. Ryan, do you see one? Okay, I knew there were some up here too. So we go 51, 54, 55, 58.9, and then down to 58.7. So that one gets lighter as well. Guys, and there are a couple other exceptions that we could pick up as well, and maybe you're seeing them. But guys, this is the big idea. What explains it? What could be happening that as we move to the right, we're adding protons? We established that. And guys, this is where this thinking is heading. So guys, up here on Z, we established that as we move to the right, we're adding protons. But now we're seeing some examples where we're adding protons, but the element gets lighter. Exactly. Guys, fewer neutrons. Because remember, atomic mass is protons and neutrons. And as we move to the right, we're always adding protons. But remember, the neutrons can change, isotopes. And so there's the possibility that as we move to the right, there's fewer neutrons, and that makes the element lighter. Does that make sense? So guys, this then is the big idea. As we move left to right, the trend is lighter to heavier. But guys, understand there are some exceptions to the rules. But guys, the exceptions are few, and we can explain them, and as a result, we're comfortable with that. So guys, this then is where we are. We now know how to identify trends down groups. We know how to identify trends across periods. In addition to that, we're also saying that if we identify a trend and if there are a few exceptions to it, it doesn't cancel the trend. It can still be a trend, especially if we can explain the couple little changes to the trend. And then guys, finally this. We can then do overall trends. So guys, where on the periodic table are the heaviest elements? On the whole thing, where are they? They're bottom right. So guys, these are the heaviest elements on the periodic table, and then up here are the lightest elements on the periodic table. Does all that make sense? Okay, so guys, this is about to get weird. The first two that we did were simple. They were straightforward. We talked about this idea of identifying trends. Guys, this is about to get a little bit wacky. So here we go. The next one that we're going to do is atomic radius. You definitely want to write this down. So the next one that we're going to talk about is atomic radius. Now guys, I think that most of you understand what the radius of a circle is. For some reason my scope, there it goes. So let's just make sure. So guys, when we draw, you don't need to do this, but guys, when we draw a circle, where is the radius of that circle? What defines the radius? Let's do this. This is not the radius. What is that? That's the diameter. So guys, what is the radius? Half of the diameter. So guys, it's this distance right here. So it's the distance from the middle to the outside. But now guys, our circle is an atom. So what's in the middle of an atom? The nucleus. What's on the outside of the atom? Valence electrons, not just any electrons, the valence electrons. So guys, this then gives us our definition for atomic radius. It's the distance between the nucleus and the valence electron shell. This is about to get interesting. So guys, here we go. Drawing your arrows. And I know that you're still writing down the definition, but when you're ready, drawing an arrow to the left, draw an arrow down in the order, and then guys, draw an arrow below pointing to the right. Then gang, we're going to label these arrows. There is not an accepted abbreviation for atomic radius, so we're just going to call it AR. All right, you ready? We are going to start, and you're going to want to write this down with me. We're going to start by going down a group. So guys, let's gather some data and let's find the trend. You ready? Guess what? Your periodic table has a back. Flip them over. Let me flip mine over. And guys, looking at the back of the periodic table, go to the key for the periodic table and find atomic radius. Do you see it there? Left-hand side at the top. Do you also notice that there's a number called the covalent radius? We're going to talk about that on Friday. Guys, right now what we're looking at is the atomic radius. So guys, do this with me. Don't worry about the units. They're angstroms. They're very, very small. But guys, find the atomic radius in any one of these groups and then go down the group and ask yourself this question. Are these atoms getting bigger or smaller? What group did you look at, Zach?
I looked at
Group 1. So in Group 1, they're getting bigger. Did anybody do a group besides Group 1? What'd you see?
3.
Group 3 over here? And what'd you see? Are they getting bigger or smaller?
It starts getting bigger.
Now be careful, you're not in Group 3, you're in the transition element. So Group 3 is over here. Yep. Give that a look. Bigger or smaller? Bigger? Guys, do you see places in the 8 groups where you go down and they get smaller? You shouldn't see any. Do you see one, David? Yeah, no. So right now, good point. And this is where this gets weird, David. You're sort of ahead of us a little, which is great. But as we go down a group, they are always, and even Liam here, I see 144, 162. Oh, here it does get a little smaller, and then we run out of data. But guys, as we go down a group, what's the overall trend? They are going from smaller to larger down a group. You guys sold on that? Okay, so let's write it in. So guys, as we go down a group, these things go from smaller to larger. Now guys, the question becomes why? As we go down a group, given what you know about atoms, why are they getting bigger? What's going on? What makes them bigger? Max, you built this beautiful thing. Why are they getting bigger? Exactly. They have to contain more electrons, but where are those electrons? They're in bigger energy levels. So guys, group number 1 is a small sphere. Period number 1 is a small sphere. Then a bigger sphere, bigger dumbbells. Well, dumbbells. Then bigger sphere, bigger dumbbells, and then the Ds. And so guys, the idea is that as we go down through a group, we're in energy level 1, small sphere, bigger sphere, bigger sphere, bigger sphere. So as we go down, we're stacking these bigger and bigger spaces on top of each other, and they get bigger. Now guys, if you're not clicking with that, let me do this. This is Bohr model, but it works. So guys, looking in group number 1, this would be hydrogen. 1 proton, 1 electron. Then if we go down below that, and if we go down to element number 3, which is lithium, now we've got the small sphere and a bigger sphere. Then if we go down again to sodium, we've got small sphere, bigger sphere, bigger sphere, and as we go down a group, we're adding layers to the onion, and these things get bigger. Is that okay? Questions on that? Okay, so guys, let's then include it this way in our notes. Down a group, the atomic radius increases due to additional energy levels. Now, David, we're going to go where you went, and this is where this gets a little bit crazy. So guys, down a group, we're sold on the idea they go smaller to larger. You ready for this to kind of get weird? Guys, do this one with me. We're now going to talk about across a period. And again, guys, remember, we've talked about this idea that if we see exceptions to the rules, we're comfortable with that. We are looking for the overall trends. So guys, allow your eye to scan across a period. Doesn't matter which one. What happens to the size of these atoms? Do they get bigger or do they get smaller? They're getting smaller. Guys, the trick is we've got to understand why. So let's write it in and then let's talk about it. So guys, these go from larger to smaller as we move from left to right. So guys, the question becomes why? Let me explain to you the answer. So why do these get smaller as we move from left to right? Well, guys, think about what we're doing is we're moving from left to right. So guys, as we move from left to right, we're adding protons to the nucleus. We're also adding electrons, but we're adding protons to the nucleus. And that's actually why they get smaller. Check it out. So guys, here we've got group number 1, and we've already said as we go down, they get bigger because we're adding energy levels. But now, guys, let's move to the right. So guys, this is hydrogen. Now let's go to helium. And guys, helium is smaller than hydrogen. Why is helium smaller than hydrogen? And the answer is because it's got 2 protons in the nucleus, and those 2 protons have a stronger positive charge, and it pulls the atom tighter together. So literally, that extra proton in the nucleus makes the protons, the nucleus, more attractive, and it sucks those 2 electrons tighter together. So then, guys, when we go into the second period, we go from lithium, and then we go over here to beryllium. And guys, beryllium's got 4 protons. 4 protons means stronger nucleus, makes it even smaller. Then, guys, we go over to boron. Boron has 5 protons, even stronger nucleus, and it makes this guy even smaller. And guys, if we kept going, carbon, nitrogen, oxygen, fluorine, and neon, they would just keep getting smaller. Then we go down to sodium, which is element number 11. When we go to magnesium, element number 12, 12 protons, stronger nucleus, even smaller. Aluminum, element number 13, 13 protons, and it gets even smaller. So guys, the idea is that as we move left to right, we're adding more protons to the nucleus, and that makes the elements smaller. Do you get the idea? So guys, this was actually really cool. I started teaching this way probably 3 or 4 years ago. And after I taught this to a group of students, I had this girl come up. She didn't raise her hand during class, but she came up to me after class. And she said, Mr. Neber, I want to show you something because this is the way I understand this idea of atomic radius. And I want to make sure it's right. And she showed me her class notes. And she had drawn this representation on her class notes, and I was like, oh shoot, that's brilliant. Can I steal that and share it with my students? She's like, yeah, guys, let me show you what she drew. So she did this. So she grabbed her periodic table that you guys are taking your notes on, and what she did is she drew lines, and she said across the first period, they get smaller. Then when you go down to the second period, they get bigger and then smaller. And then the third period, bigger and then smaller. And then the fourth period, bigger and then smaller. And it just keeps going. And I was like, oh shoot, that's brilliant. Because guys, look, it shows us they're getting smaller as we go to the right, and they get bigger as we go down. And that's exactly the trend. Do you understand the idea? So guys, let's say it this way then. So what is the trend in atomic radius? And going across a period, they decrease because of an increased nuclear charge. And I'd encourage you to throw that in your notes as well. So guys, this is where this gets a little different then. And Zach, you mentioned that idea of, is it like reading a book? And here's where you've got to be careful. Guys, where are the biggest elements on the periodic table? Bottom left. Guys, these dudes down here are the big fat slobs of the periodic table. And the small elements, the compact elements, are up here. So these are the big fatties, and these are the small compact ones in the upper right. So Zach, at that point, this is where the reading the book analogy sort of falls apart. So guys, the big fatties are bottom left. You guys good on that? Anything there you want to talk about? Because this is a very important idea. You okay? All right. So guys, let's keep going. The next trend that we're going to talk about, and guys, we're actually closing in. This is big, but we're kind of moving towards the end of the day. Guys, the next one that we need to talk about is electronegativity. This one's huge. This entire unit hinges on electronegativity. So guys, rather than have you try to figure out these trends, the first thing that we've got to do is define this. So I'm just going to give you the things that you need to know about electronegativity. Write them down, and then it'll make more sense as we talk about it. So guys, first of all, what is electronegativity? And electronegativity is defined as an atom's ability to steal electrons from other atoms. It's stealing power. What's that? Oh, seriously? Oh, we did talk, didn't we? So guys, when we think about electronegativity, if you can just keep the idea of stealing power in your mind, that'll be great. But guys, this is where this gets, there's one more term, and don't just write it down, just trust me, write it down. We'll talk about it in a minute. All of this depends on what is called shielding. And guys, let me just define it for you, and it'll make sense in a minute. Guys, shielding is interference caused by electrons that surround the nucleus of an atom. And guys, I know none of this makes sense, but it will in just a minute. So I'm going to zoom out. Same material. I'm just sort of resetting the stage. You guys okay? So guys, the next thing we need to do then, let's draw our arrows. And then through the brilliance of PowerPoint animation, you're all going to understand electronegativity. So draw an arrow to the left, draw an arrow underneath. There is not an accepted abbreviation for electronegativity, so we're just going to call it EN. All right, so guys, this is where you should be in your brain. Electronegativity is stealing power, and it has something to do with this idea of shielding, which doesn't make sense, but it will in a minute. But guys, understand, when we say stealing power, we need to say stealing what? And what we're talking about is stealing electrons. So electronegativity is a measure of an atom's ability to steal electrons from other atoms. Y'all caught up with the idea? Check this out. So guys, what is electronegativity? Can I get rid of this? It's going away. Guys, electronegativity, do you still need it? Electronegativity, guys, is the ability to steal electrons. So guys, check this out. So what we're going to do is we're going to grab two atoms and we're going to figure out how able they are to steal electrons. So to do this, I grabbed the smallest element on the periodic table, and that would be hydrogen. 1 proton, 1 electron, that's hydrogen. So then, guys, I picked another element to be our other example, but instead of sodium, which I've already drawn for you, I went all the way down to potassium. And guys, potassium's got 19 protons and 19 electrons. So guys, here's the question. Which one of these two atoms, hydrogen or potassium, is a better electron stealer? Which one is more electronegative? So guys, to answer the question, you got to understand what's going on. So let's start with hydrogen. So over here we've got a hydrogen atom, and this atom wants to steal this electron. So guys, here's how this goes. Which part of the atom, the proton or the electron, is going to be attracting this guy? Does the proton attract the electron, or does this electron attract that electron? Why the proton? Because this is positive, and that's negative, and positives attract negative. So guys, here's what happens. This proton reaches out and pulls this electron in towards the atom. So the proton is doing the pulling. But guys, what is this electron, the one that's already in hydrogen, what is this electron doing to that electron? It's pushing away. Guys, that's shielding. Do you now understand shielding? So guys, shielding is the interference. So the nucleus is going, hey, electron, come over here. And this proton's going, you're not coming over here because I'm negative and you're negative and I don't want you over here. And that's what shielding is. So guys, this is what's going on in hydrogen. Now let's go over to potassium. Guys, potassium's got 19 protons. And all 19 of these protons are like, this huge positive, pulling that electron back, all sorts of positive pull, stripping on that electron. But then guys, what are these 19 electrons doing? They're all pushing, all sorts of shielding, going, you're not coming over here because 19 of us are also negative, pushing away. So guys, here's then the question. Which one wins? So we've got a small little hydrogen atom, only one proton in the nucleus, so not a lot of pull, but only one electron, so not a lot of shielding. Guys, over here, we've got 19 protons, huge pull, but we've also got a ton of shielding. So which one wins? The smaller hydrogen or the bigger potassium? You ready? It's surprising. Guys, it's actually the hydrogen. Hydrogen is better at stealing electrons than the potassium is, and as a result, it gets the electron and it sparkles. But the idea, guys, is that the smaller atom will always win. And guys, this is really counterintuitive, but it's worth writing down in your notes. Guys, underneath where you have electronegativity, small guys are always strong guys. When it comes to stealing power, the small guys always win. Smaller is always stronger because they have less shielding. So guys, let's then turn that back to your notes and let's get this all filled in and then identify the trend. So guys, the idea is this. We understand that electronegativity is stealing power, and now we understand that smaller is stronger. So guys, now let's look at the trends on the periodic table. But rather than look at the numbers on the periodic table, guys, let's look at the trends. So we now know that smaller is stronger. So guys, I have a question for you. Why did I teach you atomic radius first? What does atomic radius tell us? How big they are. And guys, if we know that the small ones are at the top, if the small ones are at the top, are these going to be weak or strong given what you just learned? They're going to be strong. Those are your strong guys. And then guys, as we go down, they get larger and therefore they get weaker. And again, it seems sort of backwards, right? But guys, the smaller guys have less shielding, and so they're stronger. And then guys, as we move from left to right, these are the big ones, so these are the weak ones. And as we move to the right, they get smaller and they get stronger. So guys, you ready? Where are the butt kickers on the periodic table? They are top right. Guys, these are the elements on the periodic table that are crazy, 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 crazy reactive. So let's do this. Look up their electronegativities. So where do you find this? Guys, you'll notice electronegativity is it's the number in the upper right-hand corner. So the high and the top of the scale is 4. So guys, looking at their electronegativities, do you see that those numbers in the upper right-hand corner are the biggest numbers? But what's weird up there? A lot of them are Unknown. And it's not just that they're unknown. Guys, check this out. If you look at helium, what is the electronegativity of helium? It's a dash. And that's the idea. Say it again, Cole. Exactly. Because they're noble gases, they can't take in electrons because they have nowhere to put them. So guys, if you allow your eye to scan down the noble gases, you'll see that they don't have electronegativities. There's a dash, meaning they don't have electronegativities. But now you should have a problem with that. Do you guys have an electronegativity for krypton and xenon? Yeah, I do too. Guys, it turns out that we can actually force krypton and xenon to take in electrons. It's really fancy chemistry. It doesn't apply to us. But guys, the overall idea is this. These dudes do not have electronegativities, the noble gases, because they have nowhere to put electrons. So the highest electronegativity on the periodic table is fluorine. Guys, fluorine is terrifying. If you take fluorine and turn it into an acid, it is so corrosive that you can't even store it in glass because it eats through the glass and ends up failing the bottle. The only place that you can store fluorine in its acidic form is actually in wax containers because it can't attack wax. It'll even eat holes in glass. It's terrifying stuff. So guys, fluorine is the most reactive element on the periodic table. What about the least? Where do we find the big fat weaklings? Bottom left. Guys, francium and cesium and radium. Guys, seriously, everybody beats those guys up. They're so big and fat and weak that they just can't hold their own and they just get pummeled and lose electrons like crazy. Yeah?
So, has fluorine ever been used as like a weapon before?
Have we ever weaponized fluorine? Not really. So the problem with fluorine is it's hard to isolate. Like it wants electrons so bad that it's going to grab electrons from anywhere they can find it. And so it's hard to use as a weapon because it just grabs a hold of electrons in storage, and as a result, you can't use it to grab electrons when you want it to later. But there are really cool things we do with fluorine. One of them is non-stick coatings for pans. If you've ever bought like a saucepan or a fry pan and it's got a non-stick coating, it's actually made out of fluorine. Because what they do is they take the fluorine and they bond it to other molecules, and it grabs electrons so strong and locks together that food can't stick to it because it's stuck to other stuff already. And so we do really interesting stuff with fluorine, but not that particular thing. So, you guys good on this idea of weak and strong and all that good stuff? Okay, so guys, we're now going to roll to the end of the day. You ready? The last one that we need to do is called ionization energy. This goes quick. So guys, last trend, ionization energy. Ionization energy is the amount of energy needed to steal an electron from an atom. The amount of energy needed to remove an electron from an atom. So guys, you can think of this as being keeping power. But here's the deal, guys. The trend is exactly the same as electronegativity. The things that make atoms good stealers also make them good keepers. So it's still smaller is stronger. So as a result, as we draw in the arrows, we've got left, we've got down, and we've got to the right. We're going to label these IE for electronegativity. And guys, the trends are exactly the same. Down a group, it goes stronger to weaker. And across a period, it goes weaker to stronger. It's exactly the same trend as electronegativity. We'll talk more about it on Friday. But guys, for now, just understand we measure stealing power as electronegativity. Keeping power is ionization energy, and we're going to talk all about this more on Friday. So guys, there's your trends. How you guys doing? You all right? So guys, we've got about 5 more minutes and then we're done. But we do have one more thing we need to do. You guys okay? Okay, so guys, last thing we need to discuss is this. We've talked about the parts of the periodic table. We know that we've got the groups, we got the periods, we got the alkali and alkaline earth metals, transitions, halogens, noble gases, all that other stuff. Guys, there's one more thing that we need to discuss on your periodic table. What I would encourage you to do is this. Take your notes page and just flip it over on the back. This works better. Guys, there's one more thing we need to talk about on the periodic table. One more way of setting up the periodic table, and then we're all done. Can this go away? All right, so gone. So guys, the last thing we need to do, and you might want to scratch this at the top of your notes, metals and nonmetals. So guys, on your periodic table, you're probably still looking at the back of it. Did you guys notice this heavy blue stair step that goes through your periodic table here? Guys, let's do this. Take that heavy blue stair step, flip your periodic table over onto the front, and trace it. So guys, it actually looks like this. So take your periodic table on the front and trace in that heavy blue stair step. So it starts at the left of boron, it goes down and over, down and over, down and over, down and over, and then all the way down. See, mine actually has it on the front and not the back. For some reason on your table they put it on the back and not the front. But you want it on both. So guys, that heavy blue line actually separates the metals from the nonmetals. So you guys, again, we're sort of back in just jotting notes down mode. You're going to need all of this for the lab that we're going to do on Wednesday. But guys, this is the stuff you need to know about the metals and the nonmetals. Did you get your line drawn in? Okay, so the first term you need to know is this. It's metalloids. Guys, metalloids are not metals and they're not nonmetals. They're in between. These are the elements that are above and below the staircase. So the metalloids are boron, aluminum, silicon, germanium, arsenic, antimony, beryllium, and polonium. Those are the metalloids. They're kind of like metals. They're kind of not like metals. They're sort of stuck in between. Just a term you need to know. So guys, if those are the metalloids, now we need to talk metals and nonmetals. So guys, metals are on the left-hand side of that stair-stepped line. So guys, if you look at this from a distance, you're probably going to notice that most of the elements on the periodic table are metals. So if this is the line that separates them, everything over there, including the F sublevel, are metals. So guys, these are the things you need to know about metals. First of all, they don't have very many valence electrons. We know that these have 1, these have 2, these have 2, these have 2. So guys, the metals don't have very many valence electrons. 1 and 2 and sometimes 3. But guys, just a second, Zach, what about this? Are the metals, if the metals are on the left-hand side, are they relatively big or relatively small? Check your notes, big or small. As we go to the right, they get smaller, so these are bigger. So guys, the metals are big. So if the metals are big, are they weak or strong? Weak. So guys, the metals are big and weak. And as a result, they give away electrons like crazy. Guys, that's what allows them to conduct electricity. All electricity is a flow of electrons, and the metals are just giving away electrons, and that's what lets current flow through them. Zach, go ahead.
So if you made a solid, would it be?
It is, yeah, actually, if we have time, we can look it up. Metallic hydrogen, you have to cool it down to just like a couple degrees above absolute zero. It looks like aluminum. It looks like a shiny metal. Yeah, it's really interesting. So guys, this is what you need to know about metals. They are big, they're fat, they're weak, they don't have very many valence electrons. And guys, as a result of all of these things, here are the things you need to know. First of all, they form cations. When metals lose electrons, cations are positive, so they form cations. In addition to that, they conduct heat and electricity. And then, guys, they tend to be solids. Notice that solid is black on your periodic table. They tend to be solids, and their solids are hard, shiny, ductile, and malleable. And once you've written those down, I'll tell you what they mean. And then we're going to do nonmetals, and then we're done for the day. Did you look it up? Hydrogen?
Yeah.
What, did it show you a picture?
Kind of. It was like between two things, and it was like just a tiny little piece of it.
So you couldn't really tell?
Yeah.
What did you look up?
Metallic hydrogen.
Oh, that might be why. Because technically, hydrogen is a metal, even if it's a gas.
Solid.
I just looked up solid hydrogen. Oh, I'll bet you that's the same picture.
Yeah.
Is that the one that you saw?
Yeah.
Yeah. No, that can't.
Why did such small amounts of it?
Oh, shoot. They even have solid helium. That's really cool. I'll show them in a minute. So, guys, let's talk about what these words mean. So, hard obviously means hard. Shiny means reflective. Guys, ductile means that when you pull on it, it's like taffy. It doesn't break, but it stretches. So, ductile means you can stretch it without breaking. And then, guys, malleable means if you smush it, it doesn't shatter. So, like if you took a piece of aluminum and hit it with a hammer, it would smush without shattering. That's what malleable means. So, metals tend to be hard and shiny, ductile, which means stretchy, and then malleable, which means smushy. You guys okay? Okay, so let's wrap this up. So then, guys, at the other side of this thing, we've got the nonmetals. These are on the right. And the nonmetals are just the opposite. They have a lot of valence electrons. They're small and strong. And guys, because they're small and strong, they are electron gainers that tend to form anions. And guys, I know we're hurrying, but may as well just get them scratched down. Here, let me just wrap this up. Then, guys, they're anions. They insulate. They don't conduct heat. They don't conduct electricity. And they can be solids, liquids, or gases. If you look at the colors on your periodic table, you'll notice the black and the red and the blue guys are over here. Solid, liquid, and gas. And their solids tend to be brittle. They're not very squishy. They tend to shatter rather than smush. So guys, there you have it. What we're going to do to wrap up the day is I'm giving you your homework packet for the unit. Guys, we're going to do homework assignment number 1 and grade it on Wednesday. Then, guys, we're going to do a lab on Wednesday, which actually is going to review everything you learned today. It's a good lab. You're going to like it. And then we'll also get you your test back on Wednesday. But that'll do us. So guys, I would encourage you to you're welcome to tuck your notes away, but you may want to keep them at hand. So guys, we're doing homework assignment number 1. Notice that it's 3 pages. Some of it's just filling in the blanks. Some of it you're drawing pictures. But guys, I'll tell you right now, some of these questions are actually going to require that you don't just jot down your notes. You think about the things that you've learned. There's some application here. Guys, the answers are already posted on our website. Spend some time. We've got 15 minutes right now, which is awesome. Did I give you too many? So guys, we've got 15 minutes right now if you want to dig in and get going. And again, if you haven't taken the test yet, the electrons test, today after school, you're welcome to come. You don't need to let me know. If that doesn't work for you, I'd strongly encourage you to make other arrangements. So guys, the time is yours. Dig in. Let me know if I can help. That'll do us. Oh yeah. Here, and guys,